Good afternoon, everyone. We're gonna start our discussion of the. Let me go back to white. We're gonna start our discussion of the Laplace transform. And before we can start talking about the Laplace transform, we have to talk about singular functions. In this lecture, I'm gonna introduce singular functions, and I'm gonna provide you with the motivation of why are they necessary, right? And how they play a big part in introducing the Laplace transform. But first, let's step back a bit and let's go over the big picture quickly. What is the Laplace transform about? What are we doing here, and why are we doing it? The Laplace transform is what is called a reparametrization of functions, right? What does reparametrization of a function mean? So we have functions f of t, g of t, k of t. All those functions have a parameter. The parameter is time, right? Which is fine. A lot of the problems we faced in this course have to do with representing signals in time and figuring out how circuits behave when those signals are inputs to those circuits and what the response would be. So we try to find the response. Like assume this is an input, bunch of inputs, and then we try to find responses, and the responses are also functions of t. Everything is written as in terms of functions of t. Everything varies with respect to time, right? The Laplace transform is a method of reparametrizing the function so that the function depends on some other parameter, f lambda. That is not time, that's something else, like g lambda, let's say, or hs. That's all what reparameterization mean. Now this extra parameter, this alternate parameter could be something else, could be frequency, for example. But it doesn't have to be frequency. This is just an alternate parameter that's different from time. The key thing is that for this to be meaningful, whatever alternate parameter we find out, let's say f, call it f zeta, let's say, and random parameter, I should be able to switch back and forth from this reparameterization to the original representation in the time domain. As long as I can transform from the time domain to this reparameterization, and then I can go back at will, right? Things will be orderly and fine, right? Why do I want to do that? Why do I want to reparameterize? Well, what have we been doing since day one in this course? We've been, solving circuits. And what does solving circuits mean? I mean, what did we do in the first couple of weeks? We were solving differential equations, right? To get the responses and all of that. The incentive for reparameterization is perhaps if we do this, if we move from t as the parameter to some other parameter and transform the signal or the function to that other parameter, maybe it will bias that solving of the differential equation will become easier. If we can make the solving of the differential equations easier, then we have achieved a successful transformation, and the transformation would be worth it. If I introduce some kind of transformation between the t parameter, time parameter, and some other parameter that makes solving systems harder, solving differential equations harder, then this transformation is pointless, right? We only care about transformations that make our lives easier. That's the only reason we kind of bother at all. with those kind of things. All right. So the Laplace transform is one kind of reparameterization. It's just going from the t as parameter to some other parameter called s, right? There are, by all means, it's not the only way to reparameterize functions. There are other ways. One famous way to do that is the Fourier transform, for example, which is a different transform. It is related to the Laplace transform, but it's different. And there are other transforms. When you go to the discrete domain, there's the Z transform, for example. But there are also other continuous transforms, right? So that's the big picture. We're going to introduce this Laplace transform that's going to change the parameter from t to something else. We call it s in the case of the Laplace transform. That's why we introduced s as a shortcut for j omega to prepare ourselves for this introduction of this alternate parameter s, right? And with the goal of the Laplace transform being solving differential equations easier, right? But before we can do that, before we can make that jump, we need to introduce singular functions. They are needed to define the Laplace transform properly. Okay, what are singular functions? Well, I mean, there are only two in our case for the Laplace transform. We're going to introduce what's called the Heaviside step function called u of t, which is simply defined as 1 when t is larger than 0, 0 if t is less than 0, and if I plot it, it's going to look like this. It's 0, and then it jumps to 1 instantly, right? This is clearly not a continuous function. It's not continuous around 0, right? It has a jump in it. That's why it's called the singular function, right? But it is required to introduce a Laplace transform, because when we start talking about the Laplace transform, we will not be transforming general signals. We will not be transforming f of t in general and any g of t in general or any h of t in general. We will only be transferring functions that can be written as a function of t, general function of t times u of t. General function of t, let's say h of t times u of t. We will only be transforming subsets of functions, not the whole continuous functions, just subsets of functions that can be written as a continuous function times u of t, right? Which is the first singular function that we'll be interested in. We'll also be transforming functions that are the products of a function times another singular function that we're going to introduce. The other singular function that we're going to introduce is what's called the Dirac delta function. And the Dirac delta function is a weird function. It's hard to describe, but we can study its properties. It's kind of like not a function per se, more than like a limit, the limit of a group of functions, right? So in the same way, right? So let me introduce it this way. It's if you take like a function that's like this, like a bell curve, and you continue, and the area under the bell curve is 1, and then you continue making the bell curve narrower and taller while maintaining the area to be 1 as you do this, right? What happens as you make it narrower and narrower? The magnitude is going to keep going higher and higher until you reach a point where your function can be represented as follows. It is a function that's 0 everywhere and infinite at a single point. So we represent it as an arrow like this. It exists only at a single point and it's infinite there. So if I'm going to write it down, it's going to be 0 if t does not equal to 0, and infinite if t equals to 0. It's a very weird function. It's even beyond discontinuous. It's infinite at a single point, but it has the peculiar property that because of this limiting process where we started with this wide function that has a fixed area, and we fix the area all the time while narrowing the function and increasing its height. So due to this limiting principle, so it's the limit of those sequence of curves. This function has a peculiar property that the integral, the area under the curve of delta t, is going to be 1. Okay. So this is an incredibly weird function. This is not a continuous function. It's not even a discontinuous function. It's a function that does not make any sense from the point of view of calculus, right? But some people think of it as just a shorthand. It's just something that you can just that can only exist inside an integral, and it just gives you this property, right? If you integrate it, it's going to be equal to 1, right? But we'll talk about it a bit later. But what I wanted to say, it is not a real function per se, rather than kind of like a mathematical shorthand. And to really theoretically understand this function, you have to study the theory of distributions, which is beyond the scope of this course, right? So what I'm trying to say is that there are ways to understand this function on a solid theoretical footing. It just goes deep into mathematics. But at engineering, what we do is we just can use it as a shorthand for solving problems, right? And we can adequately imagine it to be a limiting process. So we start with a wide function, short wide function that we make narrower and taller while maintaining the area underneath the curve until we get to this delta t as the limit of this sequence of functions. So that's not exactly the way it's defined properly in higher mathematics, but that's a good way for us to understand it as engineers. Because regardless of understanding all its subtleties in mathematics, it's still a very useful function to apply. It's a very useful function to use to solve problems. And that's why it was introduced, by the way, historically. Historically, it was introduced by Dirac. Dirac is a famous physicist. He taught for a long time at I believe, University of Florida at Gainesville. I think he was there, yeah. So anyway, he introduced this function, and for the longest time, mathematicians he's a physicist, of course, and he introduced it purely to solve problems. That's it. It was a useful construction to solve problems. And mathematicians for the longest time would tell him, hey, this is bullshit. I mean, this doesn't make any sense. Right? How can this be useful? And it took mathematicians like decades, like 20, 30 years, until they could put it on a solid theoretical footing. So don't be alarmed if you find it confusing. Everyone finds it confusing, right? But we can learn how to use it, okay? At least in this course. All right. So I'm gonna go there. I'm gonna discuss it more precisely, but let's go back to the Heaviside step function, right? So we need this. We need this to discuss the Laplace transform. Why do we need it? Why do we need this function? And why do we need its sister, delta t? Okay, what problem do both those functions solve for us? So I'm going to discuss this briefly now. The ultimate goal is to solve differential equations, right? Circuits are an example of linear systems. A circuit, a bunch of elements combined together, is a linear system, and a linear system always results in a linear differential equation, right? And big thing we want to always do is we want to solve those systems, right? So we can think always of we can use the block diagram representation to kind of like imagine circuits to be something that takes an input signal, let's say VNT, and the block represents something, an action that we do on the signal, and then we get an output, VO of t. So we can imagine linear systems as things that take input signals, transform them to output signals. This is input signal, and then transforms it to an output signal. This is called the block diagram view. And if you've ever used Simulink, for example, or you might use Simulink in the future, you'll see this thing used a lot, right? But that's one way you could imagine circuits or any linear system. That's one way of viewing circuits or linear system. This way of viewing it depends on recognizing that there are some input signals, and then the circuit processes this input signal. There is a machine, a block, and this generates an output signal, right? So that's a big way of imagining linear systems that you'll encounter a lot. You will especially encounter it when you go and study controls, for example, right? So, and circuits, general circuits could be, complicated linear systems. You could have million resistors, trillion inductance, thousands of capacitors, whatever, I don't care, right? But you can always, everything will go down back to if we look at everything as operations on signals, input signal, we operate on it and we get an output signal. What's the basic operation that always happens with linear systems? Well, I mean, for circuits, for example, we have the inductor, the capacitor, the resistor, right? The voltage of the inductor is L di by dt. The current of the inductor is 1 over L integral, let's say from A to T, IT dt. For the capacitor, same thing. VC is IC is C dVC by dt, right? And then VC is 1 over C integral IC dt. For the resistors, VR equals R IR, right? So from taking this perspective of linear systems, including circuits, being things, machines that take in input signals, process them somehow, and give me output signals, it's clear from just a cursory investigation here of the basic building blocks of circuits that the basic ways signals are transformed, the elemental ways signals are transformed, are through differentiation and integration, right? Differentiation and integration always arises. Differentiation and integration and multiplying by a constant, right? So if the simplest elements are those, then a combination of them is going to be a combination of differentiation, integration, and multiplying by a constant. So really the basic blocks that you can use to build any linear system is going to be differentiation, d by dt. So I have, let's say, vit, I get v out t. I have xit, I get y out t. Or integration from some constant to t something, I integrate something, in this case xit dt. Okay, so those are the two basic building blocks for any linear system: differentiation and integration, right? and we want to apply the Laplace transform to simplify those operations, to make them simpler to solve for. Because really, I mean, remember before we started studying first order systems, second order systems, we were studying DC circuits, and DC circuits only included multiplication by a constant. Because they only included multiplication by a constant, in this case resistance, they were easy to solve, right? We want to find a way where we can convert this more complicated elementary operation, linear operation, into a multiplication by a constant, and we will find that we can achieve that by the Laplace transform, by utilizing the Laplace transform. There is a big problem here, though, and this problem is that we would like those elemental transformations or operations, sorry, to be invertible, right? If I have V out, I should be able to tell what Vi is. If I have Y0, I should be able, YO, I should be able to tell what Xi is. I should be able to go both ways. So I have Vi, I should know how to go to Vo. If I have Vo, I should know what Vi introduced that Vo, right? That's a very basic property that allows us to solve systems easily, because sometimes you have the output, you get the input, sometimes you get you have the input, you get the output, right? That's very similar to if you have in linear algebra, if you have Ax equals B, that's very similar to having the matrix AB invertible. This allows you to solve for X and B easily, right? If you know B, you can find X. If you know X, you can find B, right? But there's a big problem now with differentiation. And the big problem with differentiation is this d by dt. If I have, let's say I have this signal, right? I can differentiate it and I get something else. But let's say I have the same signal plus a constant. So I have the same signal shifted by a constant. So I have a family of curves, signals, all shifted by a constant. So this is a signal plus different constants. All those different signals will, when we differentiate them, we will get the same signal, right? Why? Because d by dt of a constant is 0. So this is a big problem right now. This tells me that d by dt by itself is not invertible, right? Because this is not invertible, it complicates finding the output, the input from the output. There is always an ambiguous term that we don't know what offset level the input had before we applied the differentiation, right? So, and we need that. We need to be able to make, for us to apply the Laplace transform properly and figure out the input from the output and the output from the input, we need all our operations to be invertible. In general, differentiation is not invertible because of this basic property it has. It's agnostic to constants, constant shifts in the input function. The only way we can make it invertible is to limit the domain of functions to only functions that are multiplied by u of t. That's the sole goal of introducing u of t. It turns d over dt, converts it to an invertible function. That's it, right? So we want to, instead of taking general x of t functions, which are continuous functions, we want to only consider functions that are f of t times some special function h of t, let's say. Right? So I wanna reintroduce the argument formally now. Right? So let's say I don't want to consider any general continuous function x of t. I want to only consider functions that are continuous functions times some special function. So this is a continuous function. And this is a special function that I want to introduce. Okay, and the goal of this special function is I want to maintain the invertibility. I want to make d by dt invertible. Okay. By the way, this treatment you won't find in the textbook. I'm just I was, for the longest time I was always confused about those functions, and I found this way of understanding them, to me at least, to be the most coherent and grounded way to do that. So don't be alarmed if you don't see this discussion in the textbook. Okay. All right. So yeah. So we said we want to introduce the special function h of t to make d by dt invertible. Well, let's check. Let me take d by dt x of t. I want to now determine what this h of t needs to be. So let me take this. Let me differentiate this. So let me take d by dt f of t h of t. How do I differentiate this? Well, I mean, we have to use the product rule, right? So this is going to be f of t dht by dt plus f prime of t, well, let me write it this way, dft by dt h of t. Right? Now, the introduction of this special function can make x of t invertible, right? Depending on what we select h of t to be, right? Because I mean, it's clear that introducing the special h of t makes the differentiation invertible. Why? Because take d of dt of f of t h of t, that's clearly not equal to d of t f of t plus k, where k is a constant, times h of t. Right? Having this special h of t multiply the function makes all the difference, because now when I introduce a k constant shift to the function, I still have h of t to contend with, and this ensures that I get different results. Okay. This ensures that the function of t and the f of t plus k is going to be different. Right? Now comes the question of defining of h of t. I want to define h of t in a way that will not interfere with f. So this is the general f. Right? Well, one thing I could do, I could define h of t to be a constant. Right? But that will be useless, right? Because if I define h of t to be a constant, dh by dt will be 0, and nothing will change. I mean, I'll get the same thing. I'll get this won't be true anymore, right? Because this will be 0, right? So I want to define h of t such that it doesn't interfere with f of t. So I'll define it to be a constant for a certain region of interest, right? So that it does not change f of t within that region of interest. But then I cannot maintain it to be a constant everywhere, or else I won't achieve my objective. So I can define it to be 0 in other places. And that's how the u of t arises. Right? If I have, that's why u of t arises. It's constant for a certain region of interest where I'm interested in the function, and it's 0 everywhere, and it sort of anchors the function. It gives me the property that if I take the constant, add a constant to the function within the region of interest, I get a different result for differentiation. It maintains the invertibility of the function, right? So we can see that, like if I have d by dt, now I'm defining h of t to be u of t, f of t, u of t, right? That's let me actually do it this way. So f of t, u of t prime. Let me use the shorthand. Using the product rule, that's going to be f of t u prime t plus f prime t h of t, u of t. Right? So differentiating this is just going to give me what I expect, the differential of the function times u of t is going to give me an extra term. So this makes it such that if I take f of t plus k times u of t prime, I end up with f of t plus k u prime of t plus f prime of t ut. This does not equal this. Those two don't equal each other, right? This and this are not equal to each other. So this makes the differentiation invertible. Okay, so that's the sole reason for introducing u of t. It makes differentiation invertible. What is u prime t? Let's examine that. So how do I differentiate u of t? It's hard to differentiate u of t. U of t is a discontinuous function. I cannot differentiate it. I mean, I can differentiate it here, it's 0. I can differentiate it here, it's 0. But what's happening here? Right? So one thing we could do is we could approximate u of t, consider u of t to be the limit, consider u of t to be the limit of some family of functions. Let's call them, I don't know what you call them, m of t, let's say, k, as k approaches infinity, right? M of epsilon, let's say, as epsilon approaches 0. So let's consider it to be a family of functions that with a parameter epsilon, such that when the parameter epsilon approaches 0, we approach the Dirac delta, the Heaviside step function u of t. What could this function be? It could be anything. Well, one common thing we can define it as is this. So it's going to be m delta equals, let me write it this way. U of t, I can divide it as a limiting process of a set of functions where the parameter epsilon approaches 0 and the functions look like this: 1 over 1 plus e minus t over epsilon. Right? How would those functions look like? Those functions will look as follows. Let me draw the sequence. Let me start with small epsilon. The function is going to look like this. So this is t equals 0. The function is for very small t, negative t, right? E to the minus minus is going to be positive. E to a large number is going to be a large number, and it's going to be what? 1 over infinity is going to be 0. But then it's going to go up like this. And then what happens if t is very large? What happens if t equals 0? It's going to be 1 over 1 plus 1, right? It's going to be get to half. Right? And then for very large t, this will be e minus a very large number. It's going to be 0. It's going to be 1 over 1. It's going to hit 1. Okay? As epsilon approaches 0, the function is going to start getting narrower and narrower until at the limit, we're going to get this function. So this is going to be a family of functions that look like this. Okay, so this is a good way to approximate the Heaviside step function. It's the limit of a family of functions that look like this as epsilon goes to 0. Why is it useful to imagine the step function to look like this? Because this we can differentiate easily. And it will give us what u prime of t is. Okay? Okay, so to help with my bad drawing, I have bad drawing skills, I admit. So to help with that, to make the function that I'm introducing here, the continuous function I'm introducing here clearer, I went to Mathematica and I plotted a bunch of curves for this function, 1 over 1 plus e minus t over epsilon, where epsilon, let me write epsilon this way, where epsilon is approaching 0. So if you do that, if you plot this function in Mathematica, you'll get this family of curves. And you can see as epsilon approaching 0, we're getting closer and closer and closer to the actual unit step function, which is this. Right? So this family of functions is getting closer and closer and closer to our u of t. And why did I want to introduce this sequence of functions that's approaching u of t? Because I want to differentiate u of t, and I cannot differentiate u of t because it's discontinuous, but I can differentiate those functions. I can differentiate this. When I differentiate those functions and I plot them, I get something interesting. I get those families of curves. And something interesting happens as epsilon goes to 0. Notice what's happening here. I'm starting with short white curves that are turning into narrow tall spikes. We know this, right? We already know this. This is delta t. This is what we said delta t is. It's the limit of those sets of this sequence of functions, right? So that's interesting. That suggests that u of prime of t is delta t, and delta t is u of prime of t. Right? So that's interesting. By the way, why do I'm saying that the integral of this is 1? Right? So I'm proposing that this is delta t. For this to be delta t, the integral under this, the area under the curve should be 1. Well, the area here is going to be 1, right? Because the integral of this function is always going to be the antiderivative of the function, right? Remember the fundamental theorem of calculus, the integral of a function f of t dt equals the antiderivative of the function from a to b equals the antiderivative of the function at point b minus the antiderivative of the function at point a. I mean, this is the fundamental theorem of calculus. So if differentiation is going this way, that means the antiderivative of this function is the step function, right? So that means that the integral of this, the area under the curve of this function, is going to be the antiderivative at b minus the antiderivative at a. Let's do the integral from minus infinity to infinity. So it's going to be the antiderivative at infinity, which is 1, minus the antiderivative at 0, which is 0, which is 1. So that's why the area under the curve here is clearly 1. And it doesn't matter even if epsilon goes to 0, the area always remains 1. The spike just gets narrower and taller while maintaining the area. Okay. So using this picture, we establish now the relationship between the Heaviside step function and the Dirac delta function. So we said, let me summarize. So we introduced the Heaviside step function as a mechanism to make sure that differentiation is always invertible. This allows us to use techniques such as the Laplace transform. This allows us to solve the input from the output and so on and so forth. Right? So any signal, instead of considering general signals from now on, we will only consider signals that are f of t times u of t, right? Those kind of signals we can invert. And it's fine to consider that such signals, because in all physical signals, we don't care about what happens at, if I plot the signal with respect to t, I don't care about what happens infinitely in the past. All I care, it's fine for me to study systems where they start at 0 and then start growing. We don't need to study systems that start infinitely in the past. It's fine to study systems that start at a certain point in the past. Right? So that's why it's okay. It's not it's not a handicap to consider only signals of this form. Right? So that's one thing we talked about. And then we discovered, by looking at the sequence of continuous curves that approach this u of t, we discovered that u of prime of t is clearly delta of t, which is the Dirac delta function. Right? So we discovered this basic property, u prime of t equals delta of t, or let me write it this way, du of t over dt equals delta t. And then we know that the area under the curve of delta t, if we integrate it from minus infinity to infinity, we know that that equals 1. Again, by this argument, by taking the differentiation of those continuous sequence approximations of u of t and noting the area under them, and noting how the area under them remains constant, does not change, and the limit approaches delta t. Right? So we have this basic property. Okay? So this is fact 1. We're only going to consider functions that are multiplied by u of t or delta of t. Du of t by dt is delta t. Differentiation, the step function gives us the delta function. Integrating the delta function from minus infinity to infinity gives us 1. Another basic property we want to, so this is 3. Another basic property we want to introduce is what's called the sifting property. The sifting property states, hey, what if I'm not integrating delta t? What if I'm integrating some general function f of t times delta t dt from minus infinity to infinity? The sifting property states that this equals not 1, this equals f at 0. Why? Let's think about this. Let's say I have a general function f of t. Now this function is multiplied by the Dirac delta function. The Dirac delta function is a family of curves, is the limit of a family of curves where at the limit the width goes to 0, approaches 0, and the height approaches infinity. Right? So what's happening is that as we are approaching the delta function, everything else in the function gets multiplied by 0 except the value at 0. So only f0 is going to matter. Right? So what happens is that we end up at close to I mean, as the limit goes to, as we approach the delta function, we end up with a very narrow spike. That very narrow spike, so this is t. So as the limit approaches, as we approach the Dirac delta function, we end up with a very narrow spike that approaches infinity, right? But the area underneath it is 1. Right? But then what happens if I have f of t multiplied by delta, this whole thing gets multiplied, because the only value of that matters as the signal gets narrower and narrower, f of t is going to get more and more like a constant equal to f of 0. The only signal that matters is f of 0, the value of f at 0. So the narrower the signal is, the delta is, as we get to the final delta, we get this situation where this narrow spike is multiplied by a constant f0. What happens if I have an area under the curve and then I multiply the whole thing by a constant, right? The area is just the same area multiplied by that constant. So the area for this new thing is going to be 1 times F0, right? If I have something that has an area underneath it and I multiply everything by a constant, I end up with that same area. This new thing is going to be the same area times the constant, right? And that's what happens to f of t when I look at the Dirac delta function limit of the sequence. The f of t is going to look more and more and more like a constant, because the area of interest, the region of interest of the Dirac delta function is getting narrower and narrower and narrower, so that we get narrow enough, we get to a narrow enough region where f of t looks like a constant. And that's kind of like the reasoning for this sifting property. But this is the basic property of the Dirac delta function. Okay. So I mean, this is, I think, enough groundwork we have now for singular functions. When you study control or study this topic deeper, there are deeper things, more things to say about singular functions. But I think this is enough to know for us, for our purposes, for the purpose of circuits. This is all we need to know. This is we need to know that we're only going to deal with functions that are multiplied by u of t, general functions that are multiplied by u of t, and we always need to have u of t. Even if I give you a function, let's say cosine of t, and I tell you take the Laplace transform, there should be, in your mind, you should know that there's an implicit u of t connected to it, and then u prime of t or du by dt equals delta, and then the integral of delta equals 1. This is a basic property of delta, and then the shifting property is this. Okay, so those basic 4 facts is what we should be aware of. Okay, so let's do. I want to do an example where how do we manipulate those kind of singular functions? And manipulating those functions really all boils down always to, I mean, there's only one thing you have to remember from calculus at this point, which is the product rule. If you know the product rule, you know how to manipulate any of those singular functions. So let's say I have cosine omega t times u of t. What is the differentiation of this? Well, product rule. This is cosine, integral of differentiation of cosine, which is minus sine omega t times omega. This is how I differentiate cosine u of t, plus cosine omega t. What's u prime t now? Is delta t, right? So this is cosine omega t u prime of t, which we know is delta t. Right? That's it. What if I tell you, hey, I have e minus t minus, so another example. So let's say I have e minus t minus a. I want to integrate this function from minus infinity to infinity, or no, it doesn't have to be from minus infinity to infinity, right? Because this doesn't have to be from minus infinity to infinity. It can be from any negative constant to any positive constant. It doesn't matter, because delta t anyway is 0 everywhere, so the limits could be relaxed. But the only constraint is that one of the lower limits should be negative and the upper limit should be positive. So let's say I'm integrating this from minus 2 to 3, and there's a delta t here. What would this be? Well, this is easy. We don't have to do anything. We just have to apply the shifting property. So this is just the function at t equals 0. So this is 0 minus a. So this is going to be equal to e to the power a. Right? So this is easy. You see that. So that's another basic example. we can always, we don't only deal with u of t and delta t. We can also handle time shifted versions of u of t and delta t. So I had considered u of t minus a. So if this is u of t minus a is what? So when is 0 going to happen here? When t equals a, right? So it's going to be just time shifted a to the right. Right? So what about delta t minus a? It's the same as delta t, only it's shifted to the right to a. So this is delta t minus a, and this is ut minus a. So we should be able to deal with time shifted versions of u of t and delta t. Example, let's say I have this function, a pulse. Can I write this in terms of u of t? Yeah, I can. So this is f of t. So this is just u t minus a. This is u shifted to a minus u t minus b. You can inspect that, right? This is t. If I have u t minus a and then u t minus b, if I subtract those two from each other, I end up with a pulse like that. You should be able to synthesize pulses using the Dirac, using the Heaviside step function. Okay. Let's see what other example I could do. Of course, you can have something like this, right? If I can have something like this, right? So this is 1 and this is 2. What would this look like? Well, f of t. So f of t would be, well, clearly there's a pulse here. So this is u of t, this is 1, 2, 3. So this is u of t minus 1 minus u of t minus 2, right? But there's also a pulse here, but this is scaled by 2. So this is plus 2 u of t minus 2 minus u of t minus 3. So you should be able to look at any waveform such as this and construct it from the Heaviside step function. So we can simplify this. So this is going to be u of t minus 1 minus ut minus 2 plus ut minus 2. This is going to be plus ut minus 2 minus 2 ut minus 3. And from inspection, you could have derived this without doing this. Without considering this as two pulses, we could have from inspection derived this right away. So this is equal to ut minus 1. And then there's another step here. So this is another ut minus ut that starts at 2. So this is ut minus 2. And then we go back to 0. So we subtract. We start at ut minus 3 and then we multiply it by 2 because we're going from 2 to 0. It's okay to mix and match. So we could have a function that's a step function and a delta function. So this is 0, 1. So this f of t is going to be equal to u of t plus delta t minus 2. It's okay to mix and match u of t and delta t. Those are still allowed functions, right? Singular functions. Okay? So the general functions that we're going to deal with are always going to be functions that are a continuous function times either u of t or a continuous function times delta t or a mix of the two. Mix of the two multiplied by different constants. Those are the functions that we are going to constrain ourselves to based on the two singular functions we introduced. And within that domain, we are going to introduce the concept of changing the parameter from t and to s, which is the Laplace transform, and we're going to discuss what this implies in the next lecture. Thank you, everyone.